we prepare a porous membrane with pore size from 200 nanometers to 1 nanometers. Today, we want to speak about the fabrication of thin film layer, TFC membranes or composite membranes. In TFC membranes, we want to prepare the second layer on the support porous layer. Usually, this layer is not porous, but if we coat nanoparticles, we can produce porous second layer on the support. But when we prepare a very thin non-porous layer, this membrane is named TFC membranes. What is our aim, our purpose for preparation of these membranes? This thin layer that have thickness lower than 1 micron is selective layer. And the main layer, this is thin layer. But because this thin layer is very, very thin, have no stability, have no strength, and we must prepare this layer on the surface of a support for increasing durability, stability, and others. For fabrication of this layer, there are many methods that is called surface engineering. And the famous one is interfacial polymerization. That means the polymerization happens between two layers, between interface of two layers. Therefore, for producing of interface, we need an organic solution and an aqueous solution. That this organic and aqueous solution should not be miscible and produce two layers, and the reaction will be happening between this layer. Therefore, we call interface polymerization, and mostly used for fabrication of TFC nanofiltration membrane, TFC RO membrane, and TFC gas separation membrane. Some per-evaporation membrane, some membrane distillation membranes also can be fabricated in this technique. This technique have 3 or 4 steps. One step is preparation of this support. We need a good support for coating of this layer, and the porosity and the material of this porous support is important. Mostly, we used polysulfone ultrafiltration membrane for fabrication of NF and RO membranes. But this layer, this support can be ceramic one, can be other polymer, polyethyl sulfone, PVDF, and PTFE, and all of polymers and materials can be used, but in RO membranes, most use polysulfone because have good chemical resistance, good compactness resistance, and the price is low relatively. First, for reaction for RO membranes, we have this reaction. We want to prepare this polyimide layer on the support surface. For this, we need two monomers. One monomer, meta disposition, phenylene diamine, named as MPD. And we have a second monomer, 3-methyl chloride. This group is methyl carbonyl chloride. One monomer have 3 functional group. Another monomer has 2 functional group. Okay? Why? This is important. Why we used 3 functional monomers? Because we want to produce 3-dimensional polyimide layer. We want to prepare 3-dimensional. What is different between 3-dimensional, our network polymers, with the usual polymers? 3-dimensional polymers have cross-linking, and this causes that the produced polymer will not be dissolved, will not be melt, will not be swelling during the filtration. We want a rigid, very stable chemical resistance layer for production of a long life membrane. RO membranes usually use 5 years. We have a very good stable layer, and this layer is thin, and thin layer should be very, very strong. Therefore, because we used 3 functional monomers, we have a cross-sectional reaction. We have a main chain that this one chain connected to another chain with this cross-linkation. So, you see here and also here the thickness of this polyimide layer. For fabrication of these membranes in industrial or in lab, we first select a good support, first immerse in amine aqueous solution. This MPD dissolve in water, and TMC dissolve in hexane or heptane or isopar. That hexane and water are not miscible, produce 2 layers, separate layers. We first fill the pores of the support with aqueous monomer, and after filling, we, in the second step, put the MPD filled membranes in hexane solution having this monomer. In this step, these monomers have a very, very rapid reaction and produce a polyimide layer on the membrane surface. Use this support, but this thin layer is the polyimide layer. In lab, after preparation of the polysulfone support, we first immerse the support in MPD solution. We must give time for filling of the support pores with MPD aqueous solution. Usually 5 minutes, 10 minutes is used. After the certain time, we get out the membranes, and with a plastic roller, we remove the excess of MPD drops from the membrane surface. We remove only one time, roll, and rapidly go to the membranes to second pass, like as this, or we can put the TMC hexane solution on the membrane surface. The reaction is very rapid, complete in 2 seconds, but for completing, we usually 30 seconds or 1 minute give time for complete polymerization. And next, the excess of hexane will be withdrawn and washed with hexane for removing of the unreacted monomers. Then we put this membrane in an oven for 10 minutes in 70 or 80 centigrade for completing the reaction. That is named curing. Curing is mean that we increase the temperature for completing of the polymerization reaction. In this industrial scale, we have also these steps. We have a polysulfone support previously fabricated by phase inversion on the fabric. First, the roll feeded into the aqueous amine, and with the speed of opening and the length of this bass, we control the time of contact. Here, enter to the bass, and here exit. This distance and speed of opening can control the contact time, 1 minute, 5 minutes, or 10 minutes. Next, this roll acts as a plastic rubber and give the excess MPD solution, and in the second bass go to the organic acid chloride phase, that TMC dissolved in hexane, heptane, or organic solvents. The reaction happen, a thin layer coat on the support, and after the coating, go to an oven for completing the reaction and for drying. After that, in lab scale, we finished the membrane fabrication in this step. And the students go to the membranes for testing, for rejection and flux. But in industry, we want to, after preparation of membrane, we must change the membrane to the module. And during the module, yesterday we discussed, we must cut, prepare, envelope, roll around of the central tube and others. In these steps, the thin layer may be defect, may be destroyed. For reducing the defect possibility, we coat a third layer for protecting of the RO membranes. Therefore, the fabricated RO membranes go to the protecting coating solution. Usually is polyvinyl alcohol, PVA solution with low concentration, and only a layer coat on the polyimide layer, and go to the second oven for drying. This PVA layer, during of the application of membranes, within 1 or 2 days, will be dissolved in water and will be removed from the membrane surface. Okay? Therefore, this protective layer is not stable and will be removed rapidly. This reduces the defect possibility of the membranes. As you see, such as phase inversion, the process seems to be very simple. But such as phase inversion, we have many parameters that should be controlled, and all steps sensitive to humidity, temperature, and the purity of the materials. For example, the type of monomer is very important. When we change the MPD to piperazine, we have two monomers. We have, say, this is MPD, metaphenylenamine, in the meta position. This is MPD. When we use this monomer, we have RO membrane. But when we use this monomer, we have nanofiltration membrane. TMC is constant, all our parameters usually is constant. With change of one monomer, the rejection reduce. Rejection reduce, that we say this membrane is not RO. This is nanofiltration, because rejection of nanofiltration for NaCl is lower than RO. RO remove 99% NaCl, but NF 60, 70, 50, okay? Only with change of this monomer, you see, have similar structure, similar size, but with change of monomer, the rejection of the membranes can be changed. The morphology of support, very important. Chemistry, concentration of monomers in this slide show the effect of concentration of MPD that shows with increasing of the MPD concentration, we have a very rough surface and we have very low carbonyl groups. Therefore, with change of the concentration, the properties of this thin layer can be changed. The kinetic and thermodynamic is very important. There are many papers and books discuss about the kinetic of interfacial polymerization. The solvent is important. We use hexane, heptane is important. Contact time. In industrial scale, we want to reduce the contact time. And now, in a membrane fabrication factory, use 30 seconds for contact of MPD with support. In lab, we usually use 5 minutes, but in industry, 30 seconds. With addition of surfactant, for example, surfactant to the aqueous solution, the diffusion rate of MPD to porous increase. The surfactant reduces the surface tension of the solvent, and the MPD rapidly diffuse, and the production time reduce in the RO membrane. Therefore, we can change the kinetic and thermodynamic condition of this reaction and reduce the time and increase the flux, increase the permeability. The flux of RO membranes is related to thickness of this thin film. Some factory prepare this layer 200 nanometers, other factory 100 nanometers. And in this case, flux 50% increases. Therefore, we try to reduce the thickness of this layer, but we must prepare defect-free layer. With reducing of the thickness, the possibility of defect will be increases. Therefore, if we can prepare a thin film layer without defect, we have a good process. Keeping method, post-treatment method, curing time, curing temperature, all can influence the membrane properties. For example, in this slide, show the effect of support pore size and pore size distribution in the prepared layer. We want have this layer as a uniform. But when we have a poor surface wettability, that means the MPD cannot diffuse in the membrane pores and cannot fill all of the pores. If we have a poor surface wettability, all of the pores will not be filled with the MPD, and therefore we have not uniform coating. Therefore, in this case, the chemistry of the support is important. We must use hydrophilic supports that can absorb the water, and MPD is in the water. Okay? Therefore, we must use hydrophilic polymers such as polysulfone, polyether sulfone. The PTFE is not good. Polyethylene is not good. Okay? But if we want to use polyethylene instead of polysulfone, we must first increase the hydrophilicity of polyethylene. We must reduce the contact angle of the polyethylene by surface engineering. For example, we use plasma. With plasma, we can increase the hydrophilic functional groups on the membrane surface and in the pores. And in this case, polyethylene can be also used. Okay. The second one, the pore size distribution. When we have a big pore, the big pore will have not good layer and cause to the non-uniform. This good, but this bad, and this bad pores will reduce the rejection. Okay, we must good coating and with uniform thickness. But when we have this bad fillet, therefore we have not good rejection. Therefore, we must control all of these conditions, and there are many examples that I can speak about the effect of all of these parameters, but because we have not time, I only speak about the support structure. For fabrication of this TFC layer, some new methods is suggested. Why this method suggests? Because we want to have a better performance, better RO membrane, reduce the chemical use, and we produce the thinner layer, and therefore we will have a high flux. One method, new method, is spray-assisted interfacial polymerization. In the traditional method, we immersed the supports in monomer bath. In this case, we need many MPD volume for filling of the bath. We need, for example, 100 milliliter, but we must fill the bath 2 liters for good dispersion of the support. Therefore, one of the reasons for using spray-assisted interfacial polymerization is reducing of the chemical consumption. The second problem that MPD aqueous solution, the water, is poison for TMC. When TMC contact with water, rapidly, we have this structure for TMC. This color increases the speed of reaction, this color group. But this color group is sensitive to water. When this TMC contact with water, rapidly this color group changes to the carboxylic group. And the speed of reaction is very, very reduced. And therefore, when we have a reduced reaction, we design the experiments for 1 minute contact because we think all of TMC is in colored structure. But the entrance of the water from MPD bath to TMC bath change this color group to hydroxyl group, and the reaction speed increase, and all condition will be changed. Therefore, the second reason for using spray-assisted or electro spray or other process, that we do not want water go to the hexane TMC solution. In the spray method, we fill the MPD and TMC solution in a tank and spray to the membrane surface. The use of the materials will be reduced, and we have prepared a high flux membrane. You see here, we have a 2 spray gun for spraying of the membranes to the target. The second one, electro spraying. Electro spraying is similar to the spray method, but in this case, we use electro field for better spraying, and we usually use the electro-expand nanofiber device. Yesterday I speak. In this case, we use, instead of polymer solution in the electro-expand device, we use the aqueous and organic solution in the syringe, and with applying of the electric field, we can lower use of the chemicals also. Electro spray use very, very low amount of chemicals and produce very thin layer, you see, and uniform layer. This electro field causes to the uniform coating and very thin layer, and the obtained RO membrane with electro spraying techniques have very high flux, but the electro spraying technique is expensive, and complicated than traditional method. Therefore, in YouTube, I see that film tech company, that the famous company in production of RO membranes, now use the electro-spraying for fabrication of RO membrane as a novel technique because the use of the materials, this TMC is very expensive. 10 gram of TMC is $100. 10. It's very expensive material, but MPD is cheap. 1 kilo is $100. This 10 gram, this 1,000 gram. Therefore, TMC is very important, sensitive to humidity. We have used in laboratory, but the monomer is sensitive to humidity, sensitive to oxygen. MPD is white, but when we buy and after 2 months, change to the black. Because amine groups react with weather oxygen and change to the nitrate groups. With change of amine to nitrate, the color is changed, and the MPD after 6 months will be destroyed. TMC very sensitive to humidity. Therefore, we buy 1 gram, 2 gram, not 100 gram. Oh, new one, we want new. Therefore, new monomers is important. When we have old one, the rejection will be reduced. Show the electro-spraying. In all of this method, as I discuss in the next lecture about the fabrication of nanocomposite membrane, we can use the nanomaterials in this solution, MPD solution, or in TMC solution. If the nanoparticle good dispersed in organic phase, we add to the hexane solution. If good dispersed in water, we add to the water solution. And with spraying, we have mix of polyimide and nanomaterials that here we use the carbon nanotube. The other new technique in the fabrication of RO membranes is vapor phase interfacial polymerization. We have a liquid aqueous and liquid organic phase. We can use TMC vapor without solvents. This is also greener method, because we remove the use of hexane. In this case, we remove the use of hexane and can reduce the price also, and we can reduce the environmental problem. The first step is similar. We immerse the support in the MPD aqueous solution, remove with roller, and in second step, we do not immerse in hexane. We put the membranes in a chamber that have a vapor of TMC. We heat the TMC, change to the vapor, and in the vapor phase, react with these amine groups. In this case, the use of hexane will be reduced. We have a greener method. Support-free interfacial polymerization. The most effective parameter in fabrication of RO membrane is support properties. If we have a suitable standard support, we easily reach to high rejection. But when we have a bad support, the rejection are not good. Most of students have a problem in the fabrication of the good support as I said, the control of phase inversion condition is very hard. Therefore, some days have a good membrane, the second days have a bad phase inversion membrane, and this support influence in the RO membrane. Okay, therefore, it is better, it is suggested that we prepare support-free interfacial polymerization. But we need the support. We say that this thin layer is very thin and can be very easily teared, and we must put it on the membrane support for durability, stability. But means that support-free interfacial polymerization means that we prepare the layer separately from the support, and after preparation, we put it in a support. In this case, the effect of support, the effect of support on the properties of this layer will be removed. Okay? We need the support, and in the final step, we will use the support. But in the fabrication method, we first prepare the layer between two aqueous and organic phase, okay? Not here, not have. After fabrication of this layer, we have a suction here, and we will suction the solution, and the height of the solution reduced, come to the support surface. In this case, we have a very thin and very uniform structure. You see here, the traditional RO membranes have very rough. But in this case, the roughness is very low. And low roughness is meaning low fouling. Low roughness is meaning low thickness. Okay? Therefore, these membranes, as shown in table, have a good flux. Therefore, in the support-free, we have not the support in fabrication step, but in the final step, we put the prepared layer on a support. Another novelty in the RO and NF-TFC fabrication method is the use of new monomers, novel monomers with better performance, with better colorine resistance. Use of green monomers, bio-based monomers. In the new literatures, new papers, with that, see that the scientists suggest the new biomonomers that have good colorine resistance. One of the main problems of the polyimide-based RO NF membranes that polyimide can be reactive with chloride. And chlorine destroy the membrane. Therefore, we must remove chlorine before the RO. But in most water and wastewater, for disinfection, we must add very low amount of chlorine. Therefore, we will have chlorine in the feed of RO, and this destroy the membrane and reduce the long life of the membrane. Therefore, the membrane researchers suggest the new monomer for reducing of surface roughness, increasing of hydrophilicity, increasing of cross-link density, and others. In this review paper, most of the used new monomers are summarized, and you see that different types of the monomers, we need amine groups, and you see we have amine groups for production of the membranes. Okay? In some cases, use the hydroxyl groups instead of amine groups. In this case, we have polyester instead of polyimide, and polyester have good chlorine resistance, but usually have lower flux. With use of this polyester, we have a good chlorine resistance, but have a lower flux. In most cases, want to increase the flux with increase of the hydrophilicity. For example, when we have this Zwitter ion, this is a Zwitter ionic compound, the amine reacts, and these groups increase the hydrophilicity, and most of Zwitter ions have antibacterial properties. Also, cause to the increase the biofouling with microorganisms and bacteria. Many monomers there are in literature, use of the dendrimers. This is a dendrimer with many amine groups. Some groups react with TMC, and other groups increase the hydrophilicity, and the excess amine groups can be used for post-treatment. After fabrication of RO, we can add some brushes on the membrane surface for reducing of the fouling. In recent years, suggested a third layer in the fabrication of TFC membrane. In traditional, you see, we have a support and polyimide layer. We have two layers. Now, in 4 or 5 years ago, later, recently, suggests that we use interface layer in the fabrication of RO membrane. In gas separation, from old years, this interface layer is used for uniform coating of the TFC layer. In gas separation, we have a support interface layer that's in the gas separation named as gutter layer. In gas, we have a gutter layer, and after gutter layer, we have a polyimide layer for gas separation. In new papers, suggested that this interface layer, the second layer, can increase the membrane flux, reduce the thickness of the polyimide layer, and cause to the uniform coating of the polyimide layer. This layer can be nanomaterials, can be another polymer, such as polydopamine, polyvinyl alcohol, and others. That in this slide shows that most use nanomaterials for as this gutter layer or interface layer. And in this slide, compare the traditional membrane with the interface layer membrane, and we see that with using of this interface layer, flux can be increased 10 times. Now in the papers, asked to production of high flux RO membranes. Usually, the flux of the commercial RO membranes is 3 bar. But now say that the membranes should have 5 liters. When you submit a paper with this flux, you see that the flux of my membrane is 45 meter square per hour. That means at 15 bar, the reviewers do not accept and say that your fabricated RO membranes have very low flux. You must prepare the high flux. And if you can report 7, 8, is very, very good. Therefore, the interface layer can cause to the high flux, do not reduce the rejection, and uniform distribution can cause to the increasing of the antifouling properties. This slide compare and show the effect of this thin interface layer. Say that the use of, for example here, for use of this interface layer, increase the stability, can act as an attachment, as an adhesive, and increase the attachment of this layer. Or this interface layer do not permit for intrusion of the polyimide layer in pores and reduce the thickness. This have lower thickness than and increase the flux. Okay, and other properties. Therefore, in recent published RO membranes, the use of interface layer is very important. So there are different materials used as an interface layer. Most use nanomaterials, but for example, in this paper, use the polydopamine layer between the polyether sulfone and polyimide layer. Another novelty in the RO membrane, use of new supports. About 50, half price of an RO membrane is related to the production of support. Polysulfone is the 50% price of the RO membranes. Polysulfone, 1 kilo polysulfone have about $100, 1 kilo. But polyethylene, 1 kilo, $2. $2, $100. If we can use polyethylene polymer instead of the polysulfone, the price of the RO membranes will be very, very reduced. But I say that the supports should have good hydrophilicity. And polyethylene are not hydrophilic. Polyethylene structure is only carbon, hydrogen, okay? But in polysulfone, we have a sulfone groups, and this oxygen groups is hydrophilic. Therefore, we cannot use the polyethylene support for fabrication of RO membranes. In this case, before of the use of the polyethylene support, we must increase the hydrophilicity. For increasing of hydrophilicity, there are many methods are used for increasing chemical reactions oxidizing with permanganate, oxidizing with hydrogen peroxide. But the most used method, and in industrial scale is used, is plasma methods. Plasma is a gas medium that have many radicals and can easily oxidize everything because very, very active radicals. And only with 10 second contact of plasma with polyethylene reduce the contact angle from 120 to 50. 10 seconds. Therefore, we use cold plasma usually, and the polyethylene layer go from this chamber that have plasma, and during 10 seconds, the polyethylene can be hydrophilic and can be used in fabrication of TFC membranes, forward osmosis, RO, and others. In this slide, you see that oxygen plasma is used and hydrophilic and used for the coating of any reactant. In another study for fabrication of high performance, RO, use the metal organic framework coating for increasing of the hydrophilicity. Here use polypropylene instead of polyethylene, and for increasing the hydrophilicity, use the zeolitic imidazole framework, one of type of MOF, for production of the hydrophilic layer on the membrane surface, and then use MPD and TMC for polymerization. In this study, use the carbon nanotube forest as a support. In this study, that reached to the very high flux, about 8. I say 5 is good. It's 8, but use the very, very expensive material, but I see it cannot be commercial because the production of the carbon nanotube aligned on the surface is very, very expensive. But as a novel study, prepared this vertical aligned carbon nanotubes and prepared a very thin polyimide layer and reached to the very high flux with good rejection. But as you see, use the 15 cycle of MPD-TMC. This is a novel study, and published in a very good journal. But from industrial view, it is not economical. Also, in some studies, try to use the electrospun nanofibers as a support of RO and NF membranes. But from industrial view, as I said yesterday, the fabrication of nanofiber membranes is time-consuming and need to the higher technology, and need to I think it is not economical and it is not good, but we can prepare as a novel study. We can prepare polyamide layer on the surface of the electrospan support. Thank you. I finished the time. There are another fabrication methods, such as atomic layer deposition, physical vapor deposition, chemical vapor deposition, that in these techniques, we can fabricate polymeric and mostly inorganic layer on the ceramic or polymer support. This technology is very high technology. The resulted membranes are very good rejection, very good flux, because we can control the thickness. For example, with ALD, here show, we purge two monomers, one monomers to one monomers, with cycle, for example, with 50 cycle, we can produce 10 nanometers. If we want to reduce 10 nanometer to 5 nanometer, we reduce 50 cycle to 25 cycle. And we can produce very, very good membranes with this ALD, atomic layer, chemical vapor, or with magnetron sputtering. We can fabricate very good membranes. But the device of this sputtering device is very, very expensive and mostly used in the membranes used in electronic chip scale and used as a membranes in sensors. In sensors, we have a very low surface, and we can produce the membrane layer in very, very small scale for separation of one component from another, and then detect with a sensor detector. Or using the plasma in the fabrication of the membranes, we have a different type of plasma, and we can modify a polymeric layer on the support, or we can produce nanomaterials with plasma, or we can cause to the grafting of some monomers, some polymers to the membrane surface with plasma. And you see here, we can, such as say in polyethylene use, with plasma, we increase the hydrophilicity of the polyethylene. Also, we can increase the hydrophilicity of all polymers. We can increase polysulfone with cold plasma. We can use plasma for grafting of monomers, biomolecules. We can cause to the producing of some sites for other reactions, and many, many applications we can say for plasma. We can increase hydrophilicity. Also, we can increase hydrophobicity. If we use the hydrophobic gas, such as argon, such as ammoniac, such as SF6, we use this gas, SF6, we can add fluorine to the support and increase hydrophobicity for membrane distillation application, for membrane contact. Therefore, with plasma, with both increased hydrophilicity, if we use air, oxygen, if we use the hydrophobic gases, such as SF6, we can increase the hydrophobicity. Thank you. If any question, I can respond. What?
What is plasma?
What is plasma? Plasma, as a definition, say that the force state of the materials. We have solid, liquid, gas. The force, say, is plasma. And plasma is a gases-like medium with many radicals. These radicals produced by introducing very high voltage to a gas. For example, we have air, and in air we have a nitrogen, argon, and oxygen. When we have a electrical discharge, say electrical discharge, in this electrical discharge, we force the oxygen to give one electron to electric field. And when give one electron or gave the one electron to another, we produce radical. Therefore, we have a nitrogen radical, we have an oxygen radical. Nitrogen react with oxygen, produce nitrogen oxide, radicals, and others. Radicals is very, very active, such as ozone, and such as hydrogen peroxide, and can attach to carbon, to amine in all of materials. We can oxidize the protein with plasma.
So it is also expensive to produce?
No expensive. No expensive, very easy. We only need an electric device for high voltage. And I have in my lab, for example, we have this my hand is metal. We have some needles, and this needle is connected to the voltage, go to the membrane surface, and gas pass from between membrane and this, and with high voltage, the blue-like discharge you see. I have some videos you can see YouTube. And this blue-like gas is produced, and the plasma is produced, very easily produced, and have very different methods for fabrication of the plasma. Because I have not time, I cannot speak. We have a different technique for fabrication of a plasma. I discussed this method.
Also, one more question. Like, without the support, can we scale it up to industrial level?
Yes. Without support, for production of the nylon polyimide 6,6, the similar method is used. We have a two-phase. We have a very big bath. Water is under, and organic solution is top of layer. And one device collects the produced polyimide. And when you collect we have this bath in industrial scale. The production of the polyimide nylon is interfacial polymerization. That means we have this solution industry. Here is water. Here is organic. And one roller draw this one. And when they stretch, this with going to the left, water and organic can contact together. And we continuous takeoff and continuous production of the polyimide. Therefore, it is very easy for production.
So, like, since it produces very smooth surface and has anti-fouling properties, it's a very nice technique, right?
Yes. This in this scale, because the support cannot influence, the roughness is increases, and we can control also the thickness.
How is the hydrophile
How change the hydrophilicity with chemical function.
In polyethylene, said that by adding gallic acid and
In the polyethylene, we say that we have only carbon, hydrogen groups, okay? When we oxidize this polyethylene, that means we add oxygen groups. With addition of this oxygen group, the hydrophilicity improves. Because these electrons can interact with water and can absorb the water and therefore increase the hydrophilicity.
But in terms of reactivity, generally polyethylene is highly reactive compared to other.
Polyethylene, no have good reactivity, but plasma or permanganate is very, very strong oxidizing agent. Polyethylene used in keeping of the benzene, diesel, acids. Why? Because have very good chemical resistance. But radicals is very, very strong and can oxidize the carbon.
And one more question regarding the microplastics you said in wastewater treatments.
Yes.
Like which type of membrane generally we use it to remove? Like
To remove a microplastic. Microplastics have size macron size. Therefore, mostly use microfiltration.
even this RO membranes separation.
Yes, RO, when,
Separate these microplastics.
yes. The size for good for MF, and when MF can remove, RO also remove. But the concentration of microfiltration is very, very low. And detection of microplastic in lab have very challenges. Therefore, usually do not use MF before RO for separation of microplastic. And the aim is not removal of microplastic. The aim is removal of desalination. And if microplastic is there, RO will remove it, okay? But the size is very big, microplastic, and can be easily with filter. One of the measuring methods of the microplastic in lab is filtering from the filter paper, and after filtering with weighting of the filter before and after filtration, measure the amount of microplastic. And for this purpose, about 100 liters should be filtered because very, very low concentration. Another question? Thank you.